Welcome to Chapter 21. Chapter 21 is going to cover alpha carbon chemistry, enols, and enolates. Now, enols and enolates are primarily going to make up intermediates. We're going to be looking at reactions with various carbonyl-containing compounds. And that being said, we're not going to have to learn any new nomenclature because we did a ton of that already. We're going to be looking now, instead of at the chemistry of the carbonyl carbon, we're going to be interested in that carbon next door. This is the alpha carbon. The carbon's attached directly to the carbonyl. We will occasionally see something going on at the beta position, so it's important that you know when I say alpha and beta, that you know what carbons I'm talking about. You could, of course, continue with the Greek alphabet and have gamma and delta, etc. But we will be talking about alpha and beta positions, alpha primarily. Something that we're going to see in a lot of the mechanisms that we cover, we're going to see either an enol or an enolate intermediate. Right, an enol being an alcohol on an ene on a double bond, and an enolate is simply just the deprotonated version of an enol. Either way, what we're doing is we're trying to add something to the alpha position. Right, so it depends on if we're in catalytic amounts of acid and base or if we're dealing with strong base, but whichever route we go through, we're adding something to that alpha position. Now, we have seen this transformation here, but in the other direction, this tautomerization in organic 1. You know this reaction from organic 1 where you have a triple bond and you add water across it, and it can be Markovnikov or anti-Mark. I'm just going to look at the Markovnikov version. You know that it goes through an enol, but it quickly tautomerizes to a ketone. So this is just like a fleeting intermediate that you can't typically trap or isolate, and it continues on to the tautomer, right? It tautomerizes to the ketone. Now, that's because this is more stable, right? Most of the time, you are going to see a ketone or an aldehyde rather than an enol. Right? If you look over here, that tautomerization, it is occurring, but 99.99% of your product is going to be in that ketone. Now, there are enols that are stabilized. For instance, when you have this conjugated enol, it is stabilized by the conjugation and it is stabilized by the hydrogen bond. So you do see more of your molecules containing an enol. There's one specific example that is 99.99% or more in the other direction, and that is the phenol. Now, why would this enol be so stable? And we would see the enol more than the ketone. Aromaticity, right? We spend a lot of time talking about the wonders and benefits of aromaticity. And so if it can be aromatic, it's going to be aromatic. So most of the time, the ketone is most stable, but there are, of course, examples where you're going to have stable enols. The mechanism for tautomerization. I know this is something I teach in Organic 1, but since we are going in the reverse direction, let's go through it. Right? This can be acid or base, and it's the same two steps. Right? We're essentially just transferring protons via solvent, and we're either adding the proton or taking away the proton, and if it's an acid or base, those two steps will be switched. So in acidic conditions, the first thing we're going to do is we're going to protonate our carbonyl. This is going to have a resonance structure that is going to be important, that is going to shift that positive charge onto the carbon. right? This proximity here to a positive charge makes this alpha proton much more acidic. And so remember, this is acid catalyzed. And so we are going to get our acid back. We don't have a strong base, so water is going to be the base. And that is going to give us our enol. Under basic conditions, we're going to do this in the opposite order. We are going to see time and again that this alpha position is more acidic than you would expect. We're going to talk about that in more detail today. But it can be removed if you have a strong enough base. It is an equilibrium step, but it can be removed. So once we pluck up that proton, those electrons go down onto the carbon, right, and we make a carb anion. There's a resonance here, right, that negative charge. It's on an allylic position, so that negative charge can also be pushed up onto the oxygen. Now, in basic conditions, right, you don't have acid around, so how are we going to protonate? We're going to use water, right? Water is awesome for being acid or base when you need it to be. And so we get our hydroxide back by wrapping this up and protonating our enol. So whether it's an acid or base, right, it's the same two steps, it's just in different orders. When we look at the enol or enolate, we are going to see that you have this extra electron density on that alpha position. It's really obvious to see in the enolate here, you have that formal charge right on the carbon. But even in an enol, even a neutral enol, does have a minor resonance structure here that does put more electron density on that carbon. And of course, this is the major contributor, but this is why minor contributors are important. They can help explain certain reactivities. Okay, so we know that we're going to be looking at this alpha position. And one of the properties that makes this alpha position so interesting is the acidity of this position, the acidity of the hydrogens on an alpha carbon. We know that an sp3CH is not considered acidic, and that is still true. It's just that this particular CH is much more acidic than you'd expect it to be, and it's because, as always, the conjugate base has something stabilizing it. Anytime the conjugate base is stabilized, that's going to make the acid stronger, right? And it's stabilized through resonance here. There are two different ways that enols can attack. We're going to be interested primarily in C attack. So when we look at our enol or our enolates, we see that there is a negative charge on the oxygen or the carbon, or and that's what happens once we deprotonate, right? When the strong base comes, we have our enolate, right? Just like we saw in the tautomerization. We know that it's resonance stabilized with that oxygen. By putting that negative charge up there on the oxygen. And so you might think, okay, well, there's two nucleophilic sites. The oxygen has more lone pairs. This is where there's more electron density. But the negative charge on the carbon is less stable, right? The carbon is less happy, less okay with all that negative charge. And so we're actually going to see C attack most of the time, at least in this chapter. And so we're going to be able to deprotonate our enols or our ketones, and we're going to be able to add some sort of electrophile. Now, you can show this step of adding the electrophile from either resonance structure. It's just going to alter how many arrows you need, right? Because this structure here is the same as this structure. I mean, they're resonance hybrids. It's representing the same thing, right? It's really, the truth is somewhere in the middle. But if you are going to do a mechanism, you have to pick a place and you have to show the electron movement. It's really easy here because the negative charge is on the carbon. You can just show that bond forming. If you have this resonance structure, it's not harder. It just needs an extra arrow, right? You got to show that electron flow from the oxygen all the way through the double bond and then to the electrophile. Moral of the story: pay attention to your arrows. Is your starting structure and arrows telling the story that leads to that next intermediate? That's something that you should be paying attention to with every mechanism. All right, so talking about these acidic protons, they're much more acidic than anything on the beta or gamma position because of the resonance stabilization. There's a whole conversation that can be had here about pKa's and what makes it stronger. That's something we covered in Organic 1. First, what we want to really focus in on is base choice. There are going to be two types of bases that we are going to be interested in. They're going to be kind of our strong base and then our stronger base. We are going to talk about them as reversible and irreversible. So anything like alkoxide or hydroxide is going to fall into the reversible place. Yes, they are strong enough to deprotonate, but there is going to be an equilibrium, and that equilibrium is actually going to favor the starting materials. This is important, though. Don't discount this. We are going to look at some really interesting chemistry that relies on this equilibrium, where at any given time you only have a small amount of that enolate. There's also you can use a stronger base that's only going to move in the forward direction. Any hydride, and so we're going to use sodium hydride, is going to fall into this category. We're also going to look at LDA here in a moment. One of the reasons why NaH is such a good base is because the hydride, very strong base, is going to pick up that hydrogen, but then it's physically not going to allow it to go backwards because that H2 is just going to leave, right? It's going to bubble off and it's going to go away. So you can't go backwards if you don't have any H2 around. And so it only goes forward. So you can completely deprotonate this and have just your enolate intermediate ready for the next step. LDA is another really strong base. You don't have to know this reaction. This is what LDA looks like. It's lithium diisopropyl amide. And so that nitrogen with a negative charge winds up being much stronger than any of your oxygen bases. And so this is just a very, very strong base. And the pKa difference is the reason why this goes forward and there's no appreciable amount of reverse. So reversible, you're going to have that equilibrium. Irreversible is just going to be straightforward. It's going to be very important to have these separated in your mind because these two bases are going to be useful for different reactions. This is primarily what we're talking about here is an alpha proton to some sort of carbonyl. There are special cases, there's always special cases, right? Where you have an even more acidic proton. We're just going to say like these are, well, no, let's not call them super acidic. These are more acidic than the alpha protons that we showed up here. And it's because there's double resonance, right? Once you remove one of those protons, you can share that negative charge on the carbon and on both oxygens. More resonance structures, more stability. The more stable it is, the stronger it was as an acid. So all of these bases, right, up here are going to be irreversible when it comes to an alpha proton between two carbonyls. That will show up in another reaction towards the end of this chapter. All right, so you see, even though they're using ethoxide on this slide, we don't see an equilibrium arrow, and that's because of the pKa difference. You wouldn't need NaH or LDA. You could use it, you just wouldn't need it. So when choosing a base, right, it depends on what you want to do. And this just summarizing what I've already said. Alpha-halogenation. So we're going to finish up this video with our first reaction. Alpha-halogenation. There are going to be 3 different reactions in this section, right? And we're going to start with the simplest in my mind. We're going to start off with acidic alpha-halogenation. The overall reaction is pretty simple, so I'm just going to use acetone anytime I can. I like to do that. All right, we're going to have an acid catalyst, and we're going to have our halogen there. We're going to use bromine. This is going to allow us to put that bromine on the alpha position. Now, it works with chlorine as well. It also works with iodine. Doesn't work with fluorine. 9 times out of 10, you're going to see me use bromine, but these two are both perfectly valid. Since this is an acidic condition, right, not a strong base, we are going to see the enol, not the enolate, as our intermediate. So the first part, here we go. The first part is just going to be forming that enol. Now I'm going to do this all as one big mechanism, but this first part should very much be a review of what we just did, right? We're in acid, so we're going to go ahead and protonate. You can use H+, you can use H3O+, you could use HA. It's going to be important for this one that we actually show our resonance structure because we need the enolate, we need to go ahead and form the enol. Oh, I'm sorry. I am just wild today. Here we go. Resonance structure, put that positive charge down there on that carbon, making this even more acidic. So something like water or a weaker conjugate base of an acid could actually come in and deprotonate. So now we're going to have our enol. Now, we have seen this reaction or this type of reaction before where our double bond acts as a nucleophile, right? It is going to pick up this bromine. Now, we're not going to form that little triangular bromonium ion. The alcohol doesn't allow that. We're just going to pick up the bromine and move along. What's important to note here, though, is we do not create a carbocation. The reason we do not create a carbocation is because that pair of electrons pops back down. It's helpful in this type of reaction to know the product prediction to help you with the mechanism. Sometimes it's the other way around, but you know that you still want a carbonyl, so you know you've got to reform that double bond at some point. Now we've added our bromine. The last step here is just to deprotonate. And so what are you going to use? We're in acidic conditions, so make sure you use something that's present. If you've been using HA, use A. If you've been using hydronium, use water. You could show the Br-. At least it's something that's there. And that is going to be, I left myself so much room, how we complete that mechanism. I think this is the one mechanism where you actually do have to show the tautomerization to the enol. This is an important mechanism, very, very high potential for me to ask you about it. Make sure you practice it. Something that is important to note about alpha-halogenation is the regioselectivity. I'm now aware that you guys can see my Facebook notifications when they pop up. I'm so sorry. Okay. Regioselectivity. In that last example that I gave and on the last slide, it didn't matter if the bromine went to the right or the left. But what if it's asymmetric? The halogen will go to the more substituted side, provided there is at least one hydrogen. Right? It's not going to replace an R group, but it will replace a hydrogen. So if you have a more or less substituted side, so we have an asymmetric ketone here. If I use Br2 and acid, that bromine is going to selectively go, right? I'm going to get a major product to the more substituted side. It has to do with the enol that forms, right? If the enol forms towards the more substituted side, you get a more stable double bond, right? More substitution on a double bond is more stable. Going to the less substituted side is going to be a less stable or higher energy intermediate. So as with a lot of the mechanisms we've seen, stability of the intermediate leads to the regioselectivity of the overall reaction. This is just looking ahead to some fun synthesis. If you can put a bromine on, you can eliminate it. Once you eliminate it, you can do all sorts of things, right? You've got a double bond there now. You can do addition reactions. What I want to point out is they've used pyridine here. It's a strong enough base in this instance when you have an alpha halogen. But you could also use sodium hydroxide, potassium tert butoxide. You could use bases that you're familiar with as well, right? That's the one that I love to use, and you'll see it plenty. Adding a halogen to a carboxylic acid is a different story. Right, carboxylic acids present us with all sorts of issues because of that acidic proton. They just don't behave the same. You do not need to know the mechanism of this one, right? I love when they say it's believed. They don't feel as confident about it either. But you do need to know the reagents and how to predict the product of the Hell-Volhard-Zelinsky reaction. Right, so Hell-Volhard-Zelinsky reaction is something that you are going to be responsible for. All right, so it's going to take your carboxylic acid and in 2 steps, using bromine and PBr3 with a water workup. Important that it's 2 separate steps. That water workup is going to ensure that that OH is present at the end, but it will allow you to come to the same type of conclusion, right, where you put a bromine in the alpha position. So you have to know the mechanism of the acidic, right, of this reaction here, but you do not, acidic conditions for an aldehyde or ketone. You do not have to know the mechanism for HVZ reaction, but you do need to be able to predict the products or the reagents. This can be achieved under basic conditions. I am not going to ask you to know this one because this one, while it works, it is hard to control. It just continues on. So under basic conditions, what I want you to know is one specific reaction, and it's one that you didn't get to see in lab, but it's an interesting reaction here. It's hard to control, right? So it's hard to stop once you've added one halogen, right? So if we go here and it adds once, and you have this bromine, right? Then this hydrogen is still acidic. You have base around, it's just going to keep going, right? So it's hard to stop it at just one. So what I want you to know is the haloform reaction. So it is alpha-halogenation under basic conditions, right? So alpha-halogenation under basic conditions. And what is it useful for? It's useful for detecting let's actually write the word out, methyl ketones. If you have a methyl ketone, and we're going to just block the left side here with some additional R groups so that we only have one side with alpha protons. What will happen is if you use base and bromine, yes, it will add once. Actually, don't lose a carbon. It will add to the alpha position, but it will keep adding. It will keep adding until you have 3. And then you have something that's really interesting here. A methyl group is not a good leaving group. A methyl group with a bromine is not a good leaving group. A methyl group with 3 bromines is a good leaving group because you have so much electron withdrawing capability in all those bromines, you actually can stabilize a negative charge on a carbon. And so this falls apart. This right here will move. Oh, no, not like that. What am I doing? This right here will fall apart. Let me show you on the next slide because I know it's on there. Once you have added all of these bromines, now this is a good leaving group, much like we saw with carboxylic acid chemistry, right? You have a chlorine there. You have an OR group. You can replace it. With aldehydes and ketones, you can't replace the R groups usually, but this one, like I said, is special. You can replace it. And so in the final step, you are going to be able to get a carboxylic acid, right? Because that CBr3 falls off. It's called the haloform reaction because it forms a haloform, right? Haloform, and this is something you should know. A haloform is CX3H, right? So it's a carbon with 3 X's and a hydrogen. So chloroform is the chlorine derivative of this. Bromoform is the CHBr3, right? So it falls off and you make your carboxylic acid and you produce some bromoform or chloroform or iodoform, and this can test for methyl ketones, right? If you produce this bromoform. So it's not a great reaction for synthesis, but it is an interesting reaction to test for certain functional groups. So I would want you to know, I'm not going to ask you that mechanism, it's very long, but I would ask that you know this reaction, right? So basic conditions, halogen, work it up with acid just to make sure this is protonated, and you can take a methyl ketone to a carboxylic acid. We will start with